All right. Good morning, everybody. I'm Dionisi, and today I'm going to talk about my latest work, Lost in the Loader, the many phases of the PE file format. Work that I conducted with Mariano Graziano and Yannick Fradantonio from Cisco Talos, and Davide Balzarotti from Euracom, which is also my home institution. So as the title may suggest, today we're going to talk extensively about the portable executable file format, which is the de facto standard for programs in Windows. So I think it's worth giving a little bit of introduction to this format. It is based on the Microsoft DOS and COFF file formats and defines the headers, which are data structures that we find at the beginning of each program for Windows. In fact, each program starts with the MZ header, which nowadays is there only for compatibility reasons and only for the purpose of locating within the file where the COFF header starts. This other header contains generic information about the programs such as the instruction set architecture for which it is compiled, and whether it is a standalone executable or a dynamically linked library. After the COFF header, we find the optional header, whose name may actually be misleading because one may think that it's not mandatory, but it actually is, especially if we consider that it contains very vital information that the operating system needs in order to load the program in memory correctly, such as the entry point, which is the address of the first instruction of the program, the base address at which the program expects to be loaded, and other information, and most importantly, the data directories, which are the mechanism by which the PE file format can be extended in the future. In fact, the data directories, as of now, 16 of them are defined, and they address very specific tasks, such as import and export table, relocations, and certificate table, but more can be added in the future. Now, after the data directories, we find the section table, which define how the program looks like once it's loaded in memory. And each entry in the section table defines a section, which is an homogeneous and contiguous portion of memory that has the same permission level in terms of read, write, and execution permission. Each section is defined by its address and size in memory, its starting offset and size within the file. In theory, the format supports up to 2 to the 16th power sections, and that's a limitation due to the length of the number of section field. Now, as you can see, these are complex data structures, and the specifications are written in natural language, and they make a very good job in defining the structure of the headers, the meaning of the fields, and what are their possible values. Where the specification falls short, however, is the fact that they are not comprehensive, in the sense that they do not specify correctly what it is to be considered a valid PE file and what is not to be considered a valid PE file, at least not in all the possible combinations of values of fields. To complicate things even further is the fact that there is not really a publicly available reference implementation for how to parse the file format. And even if you want to consider Windows as your reference implementation, then that's not really publicly available in the sense that it's closed source. Now, when you take these two things into consideration, some problem may start already to arise. The fact that there is no reference implementation means that implementing the same parsing logic over and over again is the de facto rule. While the fact that the specifications are not comprehensive means that there is a lot of room for implementation choices. Combine these two things together and you end up with discrepancies, which are slight differences in how two pieces of software handle the same file. But how widespread is this problem actually? Well, if you consider the sheer amount of software that handle this format, well, you can already understand the magnitude of this problem. Classic examples are the operating system loaders and compilers, which need to speak the same language in order for the second to create valid program that the first can load correctly. But other software needs to parse the PE file format as well. We have parsing libraries, buggers, reverse engineering tools, and even antiviruses. But okay, it may be widespread, but it is severe. So what are the implications of this discrepancy problem? Well, let's try to make a case for this with two examples. Suppose that you have a program that runs under Windows 7, but not under Windows 10. Now, this already breaks backward compatibility, which is something for which Windows has spent a lot of development effort. But that's by no means the only problem. Suppose that you have a dynamic analysis sandbox, which you built on Windows 10. Well, and suppose that this program, you suspect it to be malicious. Well, your analysis sandbox simply cannot analyze this program. So these discrepancies can actually lead to evade dynamic analysis. Another example, take your favorite reverse engineering tool, and suppose that for this program gives you the wrong mapping. Now, imagine that you're already analyzing this program with this reverse engineering tool for 6 hours, just to realize that the mapping was wrong. Well, you had already lost 6 hours of your life staring at ghosts. Now, it is even more problematic if the reverse engineering tool is used in a static analysis toolchain. Basically, every other analysis that rely on this memory mapping is biased as well. As you can see, this is very problematic for adversarial settings like malware analysis and detection. Static and dynamic analysis can be evaded, and even endpoint protection software can be bypassed using PE discrepancies. And by the way, this is a real-world issue. Just a few weeks ago, the Google Threat Analysis Group found malware families which exploit the way that the differences in how Windows and OpenSSL parse the certificate table of a PE file for evasion, because a lot of tools are based on OpenSSL. Now, our work is not the first one to tackle the problem of discrepancies in PE, but even in other executable file formats. But all this other work only, in our opinion, scratched the surface of the problem, in the sense that they only documented single edge cases, and they did not provide a systematic study or a systematic approach to find discrepancies, which is exactly what we try to do in our work. To summarize our contribution, we provide the first systematic approach to discover parsing discrepancies. We created a new language to model the PE parsing routines, and we developed an automatic framework to generate samples that exploit these discrepancies. Let's now give a look to the big picture of our work. We started with some software that we want to model and that we want to compare. We reverse engineer their behavior in terms of especially their parsing routines to create models of all the operations that they perform on the input file. We then feed these models to our analysis framework, which can operate in two modes. The first one is the validation mode, which, given a model and an unknown PE file, is able to tell us whether the file is valid or invalid according to the original software, even without running the software itself. The analysis framework can also run in generation mode, which, given the models, is able to generate valid test cases. These are files that the original software considers as valid, but can also generate differential test cases by combining models of different software. These are files that are valid for one of the original software, but invalid for another one. All right, let's have a look for more in details about the constraints modeling phase. In the modeling phase, we have the objective of collecting as much knowledge as possible of all the operations that the original software performs on the PE file given as an input. And this is the only manual step in our approach. While we were performing it, we realized that there are three types of operations that software usually make on the original files. Those are structural checks that validate the file from a structural point of view, meaning that the software checks that all the mandatory headers are within the file, that the magic numbers matches, and everything on this line. We then have compliance checks, in which the software validates the file from an operational point of view. Let's just give an example. The operating system wants to check that the instruction set for which the program is compiled matches the one of the machine onto which it's about to run. The third type of operation is memory mapping. Memory mapping either loads the program in memory, as the operating system does, for example, or it creates an abstract representation of what the program looks like when it's in memory. Like, for example, what reverse engineering tools do. Now, it's important to highlight that all these three operations can be ultimately deconstructed into a set of constraints of the input file. And to encode these constraints, we created a domain-specific language, which eases the task of reverse engineering software that parse the PE file format. On the right side of the slide, we can see a model written in our language. This is very simple. It's just a software that tries to check that the input file has the right magic numbers in the MZ and the COFF header. Let's have a look to this model line by line, with checking all the type of statements in this model. The first one is the input declaration that model the fact that the software needs to read from an external source the input file. So we define the file with a mnemonic name. In this case, it's not really original, it's called file. And we define it by its file size. Then we have symbol definition statements, in which we create new symbols with mnemonic names, whose value is calculated by some mathematical operation on the original file. Then we have predicate statements, which are Boolean formulas, and these can be either terminal or non-terminal. Terminal ones are those that needs to evaluate to true for the original file to be valid. In the model, we only see terminal statements, actually, and you can determine that a statement is terminal because of the term keyword at the end. In our language, we also have non-terminal statements, and these are useful for because they can be used as precondition for conditional statements. Conditional statements are only executed if their precondition is true. And these were very useful for modeling if-then-else kind of structures. In our language, we also support loops that came really handy for modeling the constraints that the software enforces on each entry of a table-like structure, like a section table. And we even have structured types that allows the analyst to reason in terms of headers and fields rather than offsets and slides in the original file. And actually, we can define these types using C syntax. All right, let's have a look to the analysis framework, starting with the validation mode. In validation mode, we want to determine whether an input file is valid according to a model. And we do so by means of the procedural interpretation technique, which consists in evaluating each statement in the model using the data from the input file. The file is then considered as valid if all the statements in the model are true, the terminal statements are true, and invalid if even one of them is false. Right, but this does not really help us with the differential analysis problem. So we have some models and we suspect that there are discrepancies and we want to find them. And moreover, we want also to automatically generate samples that exploit these discrepancies. And that's exactly where the generation mode came handy. So examples of use cases for the generation mode are creating samples that satisfy one model, or samples that satisfy one model but not a second one. The generation mode is more complex than the validation mode, and it's based on the first stage of the approach is a translation phase from the models into SMT problems, which are something onto which we can work mathematically. The SMT problems are then fed to the Z3 backend, which can perform several types of operations, such as test case generation, differential analysis, differences enumeration, and corner case generation. We will see some of these in a moment. So the translation phase is based on the equivalence between the model and SMT problems. In particular, we can translate our models into SMT problems because each type of statement in the language has its own counterpart in SMT terminology. Input declarations, in fact, can be seen as the creation of new unconstrained bit vectors. Symbols and predicates becomes mathematical formulas to which we give mnemonic names. We handle loops by unrolling them up to a certain number of iterations. We handle structural types by translating them into offsets and slices in the original bit vector. And once the translation is completed, we take the terminal predicates and we combine them together in a logic conjunction to create the statement that the solver needs to assert. An SMT problem created with this approach has as solutions P files that are valid according to a model. But how can we use these SMT problems for differential test case generation? Well, we take two models that we want to compare, we translate them into their formulas, say P1 and P2, and we create another SMT problem given by the formula P1, logic and not P2. Now, this gives us another SMT problem whose solutions are files that respect all the constraints in the first model, but breaks at least one of the constraints in the second model. And actually, our framework is able to tell us which are the constraints that are broken in the second model. All right. We expanded this technique into the differences enumeration, in which we find all the differences between two models. This is an heuristic iterative approach, which is based on the technique we just saw, in which for each iteration, we solve an SMT problem that asserts the first model, negates the second one, but also asserts some of the previously negated constraints in the second model. This basically drives the SMT solver to find new ways to break the second problem, to create this new, basically it finds new discrepancies between the two models. Okay, in our analysis framework, we also implemented other features, such as the generation of corner cases, which tries to create as many samples as possible in order to maximize the coverage of path explored by the original software once it's fed with these corner cases. And we also implemented the customization of the content of the memory once the program is loaded in memory. So of the sample is loaded in memory. These allow us to create samples that execute valid code. We were even able to create hello world samples, so samples that print hello world. All right, let's have a look to some results of our work. So in the first place, we compared this software, the Windows Program Loader, 3 versions, XP 7 and 10, and we modeled both the kernel space and user space portion of the loader. We modeled the P file format specific signature engine of ClamAV and the memory mapping operation of Radar2 and the P module of ER. So we found discrepancies even between different versions of Windows. Now I don't have the time to explain all 5 of them. We'll just focus on one, the one that I like the most, which is that Windows 7 and Windows XP accept relocations that are meant for architecture other than the one on which the program is about to run. For example, in Windows XP and Windows 10, would consider an executable that use MIPS specific relocations, even if it's running on Intel, while Windows would discard this executable as invalid. We also found discrepancies between Windows and ClamAV, and we found 3 of them. The most interesting one, which is also the easiest one to exploit, is about the number of sections. ClamAV considers invalid all files that have more than 96 sections, while in Windows there is not really this constraint. We reached out to the developers of ClamAV, which acknowledged all the 3 discrepancies we found as bugs, and they are working on some fixes. We also ran a differential analysis for the memory mapping operations, and we found an interesting edge case that all the software mishandled. In particular, when the section alignment is smaller than the page size, Windows loads the PE file in memory as it is, regardless of its section table. This is not really handled correctly in all the software we found, which infer the memory mapping using the section table as they would do with any other executable. Now, we could not find any documentation of this behavior, so we were really not surprised that the software got this wrong, that the tools got this wrong. All right, now that we found these discrepancies, we asked ourselves, is there a way to understand whether malware authors are already knowledgeable about them and if they are already exploiting them in the wild? And to answer this question, we ran a VirusTotal live hunt campaign for which we created YARA rules that match the discrepancies that we found. All of them except the relocation one I talked about before due to the limitation of the YARA language. We ran this campaign from the 7th to the 19th of October 2020, and we estimate to have scanned something around 5 million samples, estimated from the average number of weekly submissions reported by VirusTotal. We were prompted with 467 samples that matched at least one of the rules. And it's important to highlight that all the rules that we wrote matched at least one sample. The most prominent one was the one about the section alignment that with 301 samples that potentially may trigger different mappings in the tools that we considered. The second one, second most prominent one, was the one about the 96 section, which ClamAV would consider as invalid. We actually analyzed some of them manually, and we found that some samples had 97 sections. And we believe that this was probably done on purpose. All right, a few conclusions and takeaways from our work. I think that the most important lesson that we learned from our work is that there is no one way to handle the PE file format. And even if you consider Windows as a reference implementation, then you should also specify which version of Windows you consider as a reference. Because as we saw, all of them as small quirks and small handle edge cases in a slightly different way than the others. We believe that we need more clear and formal specification for the PE file format and even a reference implementation. But this, of course, takes time and development effort, especially by Microsoft. So it's unlikely to come anytime soon. In the meantime, we advise developers of security tools to model more than one version of the Windows loader, possibly asking the user which one to employ for their analysis. We believe that our language and framework is the reverse engineering efforts that are needed to build these models. And that's the reason for which we release our framework and models in our GitHub repository. And that being said, my talk is concluded, and We'll gladly answer your questions now.
Thank you for this interesting talk. We have time for a few questions. I guess there's one question in the audience here.
Thanks for the great talk. I have a question about the models. Do you have to reverse engineer the whole loader and write them by hand, or did you find a way or consider a way to automate that somehow?
So the moment we did it manually by reverse engineering, I think it is possible to get models automatically if you have the source code. When you are modeling some closed source software, it's more complicated, I would say. But yeah, in our work we did it manually, also because we did not. It was a little bit considering the software that we tried to analyze, that were not that many. It was a little bit of an overkill to spend too much time trying to automate this. By the way, we also tried with symbolic execution at first and with taint analysis to create these models, and they did not really scale to the level of the Windows programming loader. The problem is that the Windows program loader interleaves parsing routines with very low-level operations such as memory management and anything on this line, which really complicates and makes any symbolic-based approach explode. So,
follow-up question. So you modeled them pretty precisely. Like, A, how sure are you that you modeled them correctly? And B, couldn't you use your model as a specification and maybe even generate a loader out of the models?
Very good question. So yes, we validate our models. That's where the test case generation technique that I briefly talked about came handy. So what we did is we validate both the under constraintness and over constraintness of our models. The first one is whether the models consider as valid something which is not valid for the operating system. And basically, we create the corner cases and we run them on the original software, and we check that they were actually able to run. Then to assess over constraintness, so when the model consider as invalid something which is actually valid, we took a data set of something around 9,000 samples, if I remember correctly, and we run them on the operating systems, and we validate them with our models. And we found out that they matched. So everything that our models considered as valid was actually able to run on the original system. That's how we made sure that our models were correct. For generating a loader out of our models, that's an interesting question. Well, of course, the loader, as I said, has also a lot of low-level, memory management and other stuff that it's not really captured by our models, so you would lose that. But probably, yes, you can create parsing routines using our models.
Thanks, Dario. Very good work. Actually, I'm sorry if this is in the paper, I have not read it, but this reminds me of a paper I was published more than 10 years ago on something called werewolves attacks. So the werewolves attacks were playing with the magic number, and they were trying to see if you could have a .pdf file that was actually seen to be something else, and so on and so forth. And so it was not PE related, it was more for other kinds of files. And they found out a number of things that, same thing as what you said, so there are discrepancies depending on which tool you use to open those files. And also, worse than that, for instance, for archive files, some of them were objectively broken, but some of the tools wanted to be nice, and they were actually fixing the files to actually open them properly. So I was wondering, it seems that what you have there, and the paper was well done, but it was more like a manual kind of ad hoc thing. So I was wondering, the approach you have had, could it be used to redo this kind of study, but in a more systematic way?
Yes, I would say so. We focus on the PE file format because it has direct implications for malware analysis and other adversarial settings, but we believe that the same approach can be used for other file formats. So say you just take the software that parses this file format, you reverse the parsing routines, you write down the models, and then the same operations, you can perform them automatically with our framework. So differential test case, corner case generation, and everything on this line.
Yeah, it would go one step further. It's just not within the family, but managing to let one system believe that it is actually a file. Like, this is actually the werewolf attack was specifically targeting antiviruses, because the antiviruses have a certain amount of signature per file type. So if now they think this is a PDF, they will apply the signatures for PDF, whereas maybe it's a PowerPoint or an archive file. And of course, they will not find anything because they have been fooled. So it's the same thing as what you do, but at a higher level of abstraction, so to speak.
Yes, yes. In that case, you want to model the parsing routine that decide whether which type of file this is. So basically the lib magic, let's say. And yeah, you can model that one and then use it to compare how two software do this operation.
One last question. I was also wondering if you have looked at discrepancies in how AV files, AV products parsed. I know you had ClamAV, right? But there may be differences in other products, right?
Yes, good question. No, we only focus on ClamAV for the moment. Actually, we also have a look to the P module of Yara, which is used by many antiviruses. And we also found discrepancies in that one.
All right, and since we're running a little bit late, let's thank the speaker again. Let's thank all three speakers. This concludes the section, and let's have some coffee.